This is our Project 2 video, and we decided to choose the spring box problem. And my name is Christian.
My name is Brendan.
My name is Jackie.
All right, so for the problem statement, there are two boxes with separate masses. On the left, the blue box compresses a spring an initial distance xi, and then launches the blue box to the right on a frictionless surface and hits the red box. And those two boxes stick together. And then those two boxes, while stuck together, hit the right spring on the right and compress it a distance. And that distance is what we're trying to find. This is the information we are given, and what we're asked. Both boxes start at rest. The boxes are moving to the right. The spring is identical. The springs are identical. The table is frictionless, and there's no friction in this problem. The table is level. When the boxes collide, they stick together. And the problem asks us to find the maximum distance that the second spring is compressed. All right, here are some relative quantities. We have the mass of both the red and the blue box, the initial distance of the first spring and the second spring, the final distance of the first and second spring, and then the spring constant of both springs. Here are our assumptions. Since we are on Earth, we are assuming that gravity equals 10 meters a second squared. We assume the springs are ideal. The collision is also perfectly inelastic. We also assume that momentum will be conserved due to the collisions being perfectly inelastic. And finally, we assume that the springs will maintain their shape as well as the boxes after collisions. And these are the relationships we will use. Since this is a perfectly inelastic collision, we can review our inelastic collisions and see that kinetic energy will not be conserved. However, momentum will be conserved. We will also be using the conservation of momentum and energy.
All right, so for our formulas, we will be using the potential energy for an ideal spring, which is the potential energy of the spring equals 1/2 kinetic x squared. And then and then we will also be using the translational kinetic energy, which is kinetic energy equals 1/2 mass times velocity squared. Then we'll be using the conservation of energy formulas. And the first one is the energy initial should equal the energy final. And that also means that the change in energy should be equal to 0. And it also looks like potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Some other formulas we'll be using would be momentum, which is momentum equals mass times velocity. We'll also be using the conservation of momentum formulas, which is the change in momentum should be equal to 0. And that should also be the momentum initial should equal momentum final. And we'll also be using the inelastic collision formula, which is detailed there. Okay, so for the motion of box B, we would be using the conservation of energy formulas. Here, the change of energy would be equal to 0, and that's listed at the start. Additionally, we would be using the conservation of energy formula, which is the change in energy equation, and that would be the potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. This in turn would allow us to get the overall change in potential energy, and that is listed as our answer. All right, moving on to the collision of box B and box R. we would use the conservation of momentum formulas this time. And here, the initial momentum is conserved. So we would be using the potential energy initial equals potential energy final. Then we would also use the inelastic collision formula to derive the velocity of our system, and that would be our answer. And for the compression of the second spring, we would be using the conservation of energy equations to solve for the distance that the spring compress. And here we would have, and here we would make sure that the change in energy would be equal to 0. And we're measuring for the distance compressed.
So for our physical representation, we chose to do energy bar graphs because we thought that that would be the most helpful when it comes to representing the problem physically. So we broke it down to at the start, when block B is let go, when block B is moving, when the two blocks touch, when the second spring starts to compress, and when the second spring is compressed. So at the beginning, we can see that there is all potential energy and no kinetic energy. And so that is because the block is not started moving yet, and it's just waiting to be let go. So all the energy is being stored as potential. And then for right when block B is let go, that potential energy starts to turn into kinetic energy. And then once block B is moving without touching the spring or touching the second block, it is all kinetic energy because the block is moving forward. And then once the blocks touch, that energy continues to remain being kinetic as neither of the blocks stopped at any point. Once they hit the second spring and start to compress, that energy is transferred from being kinetic and starts to be transferred into being potential energy. And then once that spring is fully compressed, all of that kinetic energy has become potential energy, and that is when you would start back at the beginning of the energy bar graph if the problem were to continue on. So for our unit checking, we chose to use the distance of the first one to double check that our equations looked good. And so as you can see, we have our equation there. If you were to plug in units for all of that, you get meters equals the square root of kilograms times meters squared over kilograms plus kilograms. Once you simplify that problem, you would get meters equals square root of kilograms plus meters squared over kilograms. Kilograms times meters squared over kilograms, and those kilograms would cancel out, leaving you with the square root of meters squared, which would be meters equals meters, which is exactly what we're looking for. For sample calculation, the numbers that we chose to plug into the equation was the mass of the red block to equal 3 kilograms, the mass of the blue block to equal 2 kilograms, and the xi, which is the initial spring compression, to be negative 0.75 meters, and that number is negative because it's being compressed backwards. Once you plug all those numbers in, you would get that the compression of the spring would be, it would be 0.5809 meters. With that, our physical reasoning conclusions were that the amount that the second spring is compressed is dependent on the amount that the initial spring is compressed. And so that if you increased xi, so the initial amount that spring is compressed, it would also increase CF, which is what we were calling the second spring compression. In addition to that, if you were to increase the mass of either block B or block R, the amount that the second spring ZF would compress would also increase. And here we have a video that just shows that. So as we increase xi, that number is also going to be increasing, and the same for when we decrease it, that number decreases. And then move on to the mass of the red block, so block MR, as the number increases, our spring constant or our spring compression decreases, and the same for the mass of the blue block. As it increases, it increases, as it decreases, it decreases.
All right, and this is a reflection. The slide just shows the similarities and differences between problems that we've done in studio as well as lecture. So for the similarities, the blue slide and the project problem share similarity because both of the problems involve a box and a spring, as well as we are both we are using the conservation of energy to find the velocity. For both the white and the blue slide, they're both involve a inelastic collision, and then for the white slide, it involves a bouncy ball and then a sticky ball. And how that relates is because with the sticky ball side and the in our project problem, we both have two similarities there when the blue and the red box stick together, as well as in the white slide when the sticky ball sticks to a wooden plank. And how these are different is because the blue side has in it a box connected to a spring, and in ours, the box is not connected to the spring, it's just touching it and using the spring. And then our problem is also a perfectly inelastic collision, and the problems to the right are not. And yeah. And this is what we learned from this problem. Overall, this problem incorporated things that we have learned all throughout this course. We use the conservation of energy and momentum as the main idea to make sense of and solve this problem. The second spring compression can be affected by the weight of either block increasing or decreasing. Another way that we have discussed the second spring compression changing is the amount that the first spring is compressed. As the value increases or decreases, so does the second spring compression amount relative to the amount that the first spring was compressed.